Welcome back to the coronavirus series here.
Bro, we literally wrote the same thing.
Okay.
I got 30 points off. I used a check. A check is a flag. Did I have to write literally a bull?
This is going to be great. I can feel it already.
And then what do you do for this one? Look, 40. This is briefly. I don't know what briefly means then, I guess.
Just give it. All right. So, are you ready? Here we go. We got the video recording already. Don't let them record your suffering. Okay. So, today we're going to learn assignment 7, which is basically building a tree from a traversal. Okay? So, as we talked about last time, come on, guys. As we talked about last time, when we were building a tree, it's ambiguous. The one sort of workaround that we did for that was with a level order traversal, but we had to make it a complete tree, and we had to use a wildcard for trees that were not complete. Now I'm going to show you a way of building the tree from just the traversals without needing any sort of wildcard. And in this class, I'm going to do post-order and in-order example. And I mean, I'll do a pre-order and in-order as well, but I'll do this one first in more detail. That way, in the other videos, I'll do the pre-order in detail. So that way, you have a thorough example of each. So, okay, I have this works. I have an example here of an order traversal, because otherwise I have to come up with one. So here we have a sequence D, B, E, A, F, C, and then we have A, B, C, D, E, C, F. So here we have two traversals of a tree. Now, is this tree a binary search tree? No, because the in-order traversal is not sorted, right? And that was the thing that somebody asked a question and somebody else answered it. The only time the in-order traversal is sorted is if the tree is not just a binary tree, but it's a binary search tree. If it has that property of it being a binary search where the left child is smaller and the right child is bigger, then the in-order traversal will be sorted. But in this case, it's not, because we got the C right there that's out of order. So ultimately, just pointing that out. But here's the thing. What could a tree like this look like? Could be a degenerate tree like that. Right? It could also be, what would be a good traversal of this? Well, we could just make that. Bam. So as you can see, it's ambiguous, right? So what we're going to do is to be able to actually build a tree, a unique tree. Whoa. What is... Oh, weird. To be able to build a unique tree from a traversal, we need actually two of them. And that's how the algorithm is going to work. We're going to use the in-order and we're going to use the post-order. And so we take advantage of the fact that the in-order traversal means that anything to the right. So if we pick a node from here, any node, pick a node that's somewhere in the middle. D, E, C, whatever. Let's just say, C?
C.
C, which C? There's two C's. Let's pick this one because it's more censored. If we pick C, what do you know about the elements that are before C on the in-order traversal? They're to the left side.
Yes.
Either on the left child or like upwards left from the parent. Similarly, to the right of that, they're bigger. So we're going to use that property of the in-order traversal to be able to decide what goes to the left and what goes to the right of each node. Then, for the post-order traversal, what do we know about the post-order traversal? Well, we know that the last node is actually the root node, right? Because it's post-order. And so, I wrote them. I see. Before I totally explain this, it turns out that that this is that. So it's definitely not sorted at all this time for sure, right?
Just to double check, are you recording?
I think so.
Yeah.
Yep, I am. Okay, so that's not what I'm actually. So now it's definitely not sorted at all. This looks not even close to being sorted, right? So here's the thing. If we're looking at the in-order traversal, as I said, any of these nodes, why is there only one C on that one? Oh, I guess I had a typo here. There's no C on that. I'm glad I'm catching these things now. Otherwise, this tree would not have built. So, as you can see here, if I go ahead and pick the E, anything to the left of the E is smaller or on the left side, per se, and anything to the right of the E is bigger or on the right side, okay? So, and then the post-order traversal, if we, and let's actually do pre-order. Just because the example that I have. Otherwise, I have to build a tree and then figure it out what it is. And we can do that in a second too. But in the pre-order traversal, what do we know about the first node of the list in pre-order? It's the root, right? It's going to be always the root. And so already there, we are guaranteed to know the sort of the beginning, at least one of the nodes' correct location, which is the first one. And so because we know that this is the root of the tree, we know that these are at some point some child or grandchild of that root node. Furthermore, if I write the pre-order sort of algorithm, it's to print out the root and then go to the left and then go to the right. So this guy, the B here, could be either to the left or to the right, right? Because if there maybe there's no left, so it goes to the right. So at this point, that's where just from this traversal, I have no idea what this tree will build. Okay. However, what I can do is I can look at the in-order traversal, right? And the in-order traversal is D, B, E, A, F, C. I know that A is the root because I just saw that in the pre-order traversal, right? Therefore, I can sort of build sort of a pseudo tree here of what it looks like now. I have D, B, and E on this side, and I have F and C on this side, okay? Because I know that these have to go to the left and these have to go to the right. What I don't know is how these three go. I don't know whose parent is who or if it's a child or whatever. But here's what I can do from that. What can I tell you, or what can you say from B and D in relation to the root? Well, you know that they're the child, right? But because B goes before D, what can you infer based on this logic? Let's see the possibilities. Okay, so the possibilities are that A is the root, and then it goes to the left. So it could be something like B and D, right? It could also be something like B and D. Or could it be like this? Could it? Why not?
Yeah, it's already on the left.
It's already on the left. So here we go A, go left, right. So then we'll hit the B, and then we'll try to go to the left. No, it could work. Yeah, because it visits them on the first go. So let's see. If we go to the pre-order is this, and then from there it's going to go nothing left, has to go right, prints out the B, tries to go left, nothing, tries to go to right, sees the D, prints out the D. So this one actually will work. Another one that could work is B and then D here. That could also work, right? Because you go to the A and then go to the B and then try to go to the left, cannot go to left, try to go to the right, you can go to the right, see the D and then print it out. So all three of these could, and there's more options. I think more combinations maybe. I'm not, well here, let me try to figure out. Oh, there's one more I can think of. That could work too. Here's the thing about all of these. I want you to notice, and you tell me, what is common in all four of these?
The levels where they're like the letters go.
The levels. Okay. Then let me give you one more case that I just thought about. Yep. So that's kind of thrown out the window because of that one, right? But something around there is what I'm trying to get to. Anybody else can think of some sort of pattern?
The order.
What about the order?
It's going A, B, D.
So like the root to left and then right.
Okay, yeah, because that's what the algorithm is. So I think you guys are seeing it, just maybe don't know how to say it. It turns out that in any of these, B always appears before D. And by that we're saying in the binary search tree, it's going to appear before in the sense that it's going to be either a left direct child and D is going to be the grandchild, or at least B is going to be on the left side and D is going to be on the right side. So we can deduce that based on this, because in all of these examples, B appeared first before D, right? D was a grandchild. But then we had this weird example. But even in this weird example, B always appeared before D. And so it turns out that we can use that to deduce that if we are looking at the left child of A, which could be D, B, or E, and we're trying to pick which of these can be the left child, well, guess what? In all of these cases, if it was the left child, it was always B. And if it was the right child, it was always B with the exception of this one, in which case it would have been the left child. So in priority, we can say left is first.
Sorry, can I understand which one of those, just the one in the square you're talking about?
Oh,
Can you highlight that?
yeah. So we are looking at these three, right? And it turns out that the next thing in the pre-order traversal is a B. And because the next thing in the pre-order traversal is B, and because we know that all combinations are the four that we listed here, or five, in all of these, I want you to notice that B goes to the left and goes first. B goes to the left and goes first. B goes to the left, and then D goes to the right, but B goes to the left out here. In the cases where B goes to the right, it doesn't matter because it always goes before D. So ultimately, either it's going to go to the first or go to the left, or both. But it's never going to go to the right and have D on this side. So it's never going to be A, D, B. Okay? And so it turns out that in the algorithm here, because B is the next thing we see, of these three possibilities, we can assume that B is going to be the child of A because of that. And so this tree becomes and some what is it? D and E are left. Which we don't know where they're going to go. They could go both to the left, both to the right. We don't know yet. But we just know that B has to be the parent of that group. So let's go ahead and copy paste that down here so we keep track of that. Okay. So now, let's go ahead and look at how this list was. We were working on this list, and we picked B is going to be the parent. Now, this is the in-order traversal, these three, D, B, and E. And before, when we had the complete list, I said that A was the root, and everything here was to the... So on, this is a D. Everything to the left of the A was to the left of it in the tree, right? So if now I'm telling you that of this subgroup, this is the root, then what's the D going to be? To the left of B. And then the E is going to be to the right of E. So it turns out that basically it becomes like that. So now the latest tree we have is A, B, D, E, and then we don't know FC yet.
So there's no way E could be underneath D.
Correct, because B it has to go before E in this sort of binary search tree style per se, and we're saying that it can if it went here or here, what would that look like? Let's see. So let's have a mysterious question mark to signify where. Well, here let's just use symbols. Let's use like no, let's use like lowercase for those. So let's say like A. So we have the following. A could go there, and maybe it's just a different color so we don't get confused. So we could have an A, a B, and then a C, D, E, F, G, and H, okay? So if we look at DBE, and we need more space than that, D, B, and E, which are coming from A, let me tell you where each of those letters would go. A, C, and D would go here. Not in that order. We'll figure that out in a second. E, B, and F would go there. And then G would go there, and H would go there. Now, what order would they go here? Well, it turns out that it would be actually C, A, D. Because, and then here would be E, B, F. That's good. I think that helps a lot, right? Yeah. Good. And so you're seeing the pattern right here. It's not that hard of an algorithm once you kind of like see the light.
Yeah, it has to just goes back down.
Yeah. So okay. So then we can mark sort of we can mark D as done. And technically, the way we would go do this here we only have one letter each, so we can sort of jump ahead and say D and E go there. But if we had multiple letters, how do we pick which one goes next? We just look at the next thing in the pre-order. So next is D, so we can say we define D to be there. Next is E, which we define to be there, so that's okay. And finally, we get C. So the next thing to look at is C. And because the next thing to look at is C, between our two leftovers of F and C, that means that C is going to be the root. And so I'll do it here, base. And then we don't know where it goes yet, technically, so I'll put it sort of in the middle. But to verify that, that's right, we will, yeah, I know. We look at the sublist here. Because C is here, there's nothing here, so that means that there's going to be no right child, and yes, there will be a left child. So ultimately, that's going to be the final tree. So now, I guess to not spoil it, let me draw a tree by hand, and then we'll do the traversals, and then we'll draw that. Otherwise, you see it and it's not as cool. Numbers or letters? What do you want? Numbers? Okay. Yeah, but see, I can only draw like 6 shapes, and then I run out of ideas. That's hard. No, that's way too hard. Get like a banana or something.
Squiggly line. Yeah. Swirl.
Okay, so I'm making them all two numbers long so that we don't get confused. I already put 11 actually. That's scary. So 33, 18. Okay, so this is a really weird looking tree, but I did it like that because I think that we can see all possibilities. So let me just very fast do the. Do you want to do another pre-order traversal example, or shall we do a post order? Post. Okay, let's do post. So then post and in. So let me do the traversals of each. Left, right, root. Left, root, right. So post order. Okay, so that's this. Well, here, I can just write it directly here. So the post order traversal of the next example is 18, 33, 71, 11, and then 77, 66, 29, 15, wow, it's long, 45, and 22. And then the in order traversal is going to be left root, so 71, right, left root, so 18, 33, 11, 22, left root, so 15, all right, left 77, 29, 66, and then 45. I think I got all of them. So that's 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. Okay. As long as I don't make mistakes doing the traversal, then we got ourselves an example. I did the traversal from I just drew a random tree. It's not sorted. It's just random. That's why the in-order traversal is not actually sorted. Yeah. And then hopefully we get the same tree. Okay. So, So post-order is the same algorithm as pre-order, except instead of going from the beginning to the end of the list, you just start from the end of the list. That's it. That's all you got to do to change the algorithm. So, and we're going to do that, of course, so you can see the example. So, I don't like how they're in 2 lines, but we'll work with it. So ultimately, let me go ahead and copy. This is like my master copy of this. I don't want to lose that. So we'll make another copy here. So what we're going to do is we are going to, what is the root then? Let me ask you, what's the root here?
71.
This is the in-order traversal. 22, that's right.
Oh, for post order?
Yeah, because
Yeah, you should start at the bottom.
yeah, because the root is somewhere in the middle here. In fact, because it's 22, we know that this is the root. Because here we found out this is the root, we identified here. Now, this whole, I guess I should give a disclaimer. This algorithm I'm showing you breaks if there's duplicates, because then you have no idea which is which. Make sense? Because like if there's 2 22s and which one's the root, then you screwed up. So I have no solution for you in that case. That's when I coded this. When I coded the solution for assignment 7, it worked. So I guess I don't know if there's duplicate letters there either. But I guess if you just follow the algorithm, assuming there's no duplicates, it'll work. So just follow the algorithm. Okay. So yeah.
If you fix it, you get extra points.
I mean, if you see if it's broken, then yes, I would. But how you fix it? How do you solve the duplicate problem? You can't. So yes, you got to set points if you fix it. Because I have no idea how you fix it. So yeah. Impossible.
You can just make it a different number.
You can do it.
And put it in later.
Right, but then that's kind of working around the issue. But even then, like, I don't know if you,
Can't you just like compare pointers?
I have no idea. But anyways, let's get through this so we can go over the test. Why are those numbers just there?
Well, you paste it as a picture. Yeah. So there you go.
Okay. So anyways, here we got our root and here's our root. So we know that everything that is green is left of the root and everything that is, come on, different color, blue. Everything to the right of that is greater than that, right? So bigger slash right, and then green is less, smaller. Okay? And yes, I know, it's not sorted. It's not a binary search tree. It's just random numbers in the tree. We're just saying it's to the left side. So I guess the word bigger is misleading, I suppose. So yeah, let's get rid of the word bigger and less. Left, sure. Okay. So the next thing that we're going to look at to pick, and I mean, we can, in fact, yeah, we can do that. Let's draw the tree, what it looks like so far. 71, 18, 33, 11, 15, 77, 29, 66, and 45, right? We got to pick the next root. The next root in the algorithm is going to be the next number in the post-order traversal from the end to the start. So that's the 45. So 45 is the next number that we're going to look at. Where's 45 in our list? I don't see oh, right here, yeah. 45. That means that that's going to be that root. And so the new tree that we're going to update, I think it's just faster if I just rewrite it. We'll forget about this side for now, since we're working on this side. 45 here, and is there anything to the right of 45? So that means there's nothing going to be here. There's no children on that side. Everything is going to be on this side.
Is that only for post order?
No, the same thing could work in pre-order. Think of a degenerate tree. 1, 2, 3, 4. Suppose you had a degenerate tree like that. The pre-order traversal of this is also going to be 1, 2, 3, 4. So you pick your root, and it becomes 1, 2, 3, 4, and then you pick the 2, and because there's nothing to the right of the 2, then there's no children here. Everything is here. So 3, 4. And then the same thing again, no here, so 4. So see that? So the same thing can happen in that tree. I'll just make it smaller in case reference. But anyways, so because there's nothing on the right side of that list, then there's not going to be any children, and they're all going to go over here. Okay, next thing. The next number to look at is 15. So where's 15 at? It's here. So now it's kind of the other way around. There's nothing to the left of 15, but there's 3 numbers to the right of 15. So the next version of this tree is going to be 45, and then to the left of that is going to be 15, nothing here, and then 77, 29, and 66 here. What?
Why was it 15? I thought we were choosing from the last.
66.
And not 66? Because this is the in-order traversal. But how we pick the next route, we look at the post-order traversal or pre-order traversal. And we can confirm. So you pick the next route from the pre or post-order traversal, and then you figure out if that goes, if the numbers after or before the route go left and right using the in-order traversal. Yeah. Okay, so now we're in this situation. So we know that one of these numbers is the root. So here, let's see the possibilities. If 77 is the next root we pick, then these two will be to the left of that. We don't know who's first, but they'll go to the left. If 29 is the number we pick, then that's easy because 77 will go to the left child and then 66 to the right child. If 66 is the next number we pick, then 77 and 29 will be left of that. Okay, so what is going to be next? We look at the post order. 29. So look at that, the middle one. So that one's easy because we can solve that quite quickly. So 45, 15, 29, and as we said, 77, 66. Technically, if 77 was like 10 numbers in there, then we would, we would figure out who goes left and right later. But because it's just one number, bam, we're done. I bet you the next number we're going to look in the post-order traversal is going to be either 77 or 66. It won't really matter at that point. Look, so there you go. And we can say they're done because technically we look at that and see that there's nothing there. That and we see that there's nothing there, right? So this is what we got so far. We got the 22. Oh, and we're done now with the right side, right? We're done with the right side of 22, right? Because there's nothing left. Now we have over here 71, 18, 33, and 11. I can't remember that. Okay? So at this point we have a lot of scrolling going on, so I'm going to copy this whole thing down here. We'll put it down here so we have space to see above. Okay. And then we're going to move this probably a little bit to this side. Since we're working on the right side now, so we need space on the right side. Okay. So the next number to look at is 11. Where is 11? 11 is here. So that means that this is going to be the next root. So you want me to copy it? Okay. Yeah, but you can just rewind the video too. I don't like that shortcut. Okay. So very less. There we go. Okay. So we picked 11, and because 11 was the last number on the list, there's nothing here, and all 3 numbers are there. Next step, 71. 71 is here. That means that 71 has no left child and has 2 right child, grandchild, whatever, 2 descendants per se, 2 right descendants. Do you want me, I guess, sure. Okay, And then for the last one, I won't draw it again. But the next number is 33. So that means, yep. And then, of course, please look at that, and we're done. Now, is that the same thing that I have? Let's see. 22, 11, 45, 71, 15, 33, 29, 18. Yep, it is the same tree indeed. So we did it. Yay. Okay. So any questions on that algorithm? Because that is essentially what assignment 7 is. You have to build both of those functions. That's it. And then you basically, in this case, you need 2 traversals to do this. So that's why in the PDF, there's 2 traversals per message. And then you have to use both of them. And then once you build the tree, then you can do all traversals, the mirror of them and whatnot, and you'll get the actual message in there. But does the algorithm make sense? Okay. Do you want me to do another example, or shall we move on to the test?
Let's move on to the test.
Okay. If not, then like I said in the other classes, I'll do the video and I'll do different trees. I won't do the same trees. All right? Cool. Okay. This is where the video ends for the internet, since I don't need to see the test. Stay safe. What's that?
Sponsored by coronavirus.
Yeah, well, I already said it in the beginning of the video, but yes, this has been sponsored by coronavirus, which, because as I said, we might actually have to do online classes, so it's pretty true, actually.